So thank you very much for coming. So thank you very much, Bert, for the invitation. It's been a pleasure to be here. Okay, so this is my full name. So in England, in London, they call me Dimi. So feel free to call me Dimi. But Gilbert knows me with Dimitri. Well, feel free to call me whichever name you want. But this is a typical long Greek name, so don't try this. But that was a very good pronunciation, Gilbert. So yes, so well done. So associate professor at Base Business School, and what I'm going to talk about today is a new line in my research, which is about the maritime search and rescue routing problem. And this is a joint project with Greg, who was my PhD student, but now is an assistant professor at Liverpool, and Tolga Bektas, who was my postdoc advisor 14 years ago. Okay, so we were quite a long time ago. And we are still very good friends with Tolga, of course, and we still collaborate in research. Right, so very few words about myself. So I'm a chemical engineer. I hold an MBA, and my PhD is in OMAR, all my studies in Athens, in Greece. So I wanted the international exposure, just to perturb the water a little bit. And I was applying for jobs. And I found that job, a research fellowship at the University of Southampton. I moved to the UK 14 and a half years ago now. And I worked with Chris Potts and Tolga Bektas on a railway organization project. So it was a timetabling redesign of the East Coast Main Line of the UK. So that project was delivered, and then for a couple of years, so we did that. So, and then I moved to Bath, assistant professor, associate professor in Bath. Had 5 lovely years in Bath, and we had the pleasure to have, so many times in Bath. I miss Bath. But I always wanted to go to London. So I got that job, that associate professorship in London in 2018. And I moved to London. And since then, I've been at Base Business School. And this academic year now is my sabbatical year. So that's why I was able to escape and come and give this seminar. Very recently, I took up a role of the associate editor for Omega, and my research is quite diverse. So I started my PhD in the resource constraint project scheduling problem. I have done quite a lot of work on VRPs, and we have published with GERAD as well. A few recent publications in job scheduling, and back then during my postdoc, I worked with Theodor Koenig and Chris Potts and Tolga Bektas on the multi-commodity network design problem. My current PhD students are working on VRPs with crowd shipping and occasional drivers, ambulance scheduling, and specialization versus generalization in hospital networks. So, feel free to let's have a chat if you are interested in these topics later. So in terms of teaching, well, I have to teach. So in terms of teaching as well, so I teach all MBA programs at Base. We have 4 MBA, so 3 executive MBAs, so 2 executive, 1 online, and 1 full-time MBA program. And of course, executive education programs, and I teach analytics and machine learning. This is what we do anyway, so this is what I teach. So enough about myself. Let's jump into the project, okay? So the project is an EPSSC/FAPESP grant application. So it stems from my grant application that I recently submitted. EPSSC is the major research council in the UK, and FAPESP is the major council in Brazil. And we collaborated with Maria Nascimento from Brazil. I know, so it's such a small world, right? But that application is in, and we wait to hear from them. And what's the problem about? What's the topic about? So we have an incident at sea. For example, we have a boat that sank. Okay, and there are some people that we need to rescue. Okay, now we do not explicitly deal with the people because we do not know where they are. All we know is this probability map that propagates through the time according to winds and currents. And you see here the direction of the winds with the blue arrows. So the questions that we're trying to answer is how many boats, how many drones, and this could be expanded to helicopters, we haven't done that yet, but how many resources do you need in general, and what are the routes that these resources need to scan the area so that we maximize the probability of finding some. Okay? But because this is a real life application, what are also the operational constraints, the operational realities that we need to take into account? Okay, so that's the problem that we are solving. It hasn't been submitted to any journal yet, so any feedback will be gold because we are drafting a paper as we go. Now, so the agenda for today's talk. So there is literature, but the literature is very fragmented. There are some papers published in ocean engineering, and there are some other papers published in our OWAR community, in our OWAR journals. Now, some key elements, some key findings that are published here sometimes can be overlooked in publications in our journal. And why is that? Because there are two different worlds. So the one doesn't cite the other, right? So very difficult to find benchmarks. And difficult to gather all the literature all together. But I'm gonna spend a little time just going through the literature in the beginning. Very briefly though. The main part of the presentation today will be two models, one MIP and one CP, one constraint programming. And both models are based on a new particle representation. So the particle representation exists, but into the modeling, we believe that it's a helpful thing to have. Okay, so it's a useful representation to have, and this is what I'm going to demonstrate today. So I said before that there are not any, so we haven't found any benchmarks yet. So we hope that there's some light in the tunnel. So there are a couple of publications that are using some data. So I will request if we can get the benchmarks. But meanwhile, we had to generate our own benchmarks. And that was a pain. And why that was a pain? Because we wanted to create realistic benchmark instances, problem instances, but at the same time complex enough that our models will struggle to solve. So how fast does the wind go? And how frequently the wind changes direction? And then how fast do the particles, move, or the probabilities move throughout the area? So we played with some diffusion models. So a lot of try and error there, a lot of try and error. I think we have something sensible, and we are going to, also make that available when we send the paper or when we submit the paper. So based on these benchmarks, I'm going to present some comparisons between MIP and the constraint programming model. And we're going to wrap it up with some insights and future research. So as I said before, this is not published work, so any feedback will be gold. Right, so the literature. So as we said, so the theory of sets dates in the late 50s, early 60s, right? So we have an object and we have a searcher. So, and the movement of the object and the movement of the searcher are totally independent. So the object doesn't try to escape the searcher, and the object doesn't try to meet the searcher either. So these two are independent. I just wanted to mention. But this is what floods up in the literature, moving targets. So you're going to see, so moving targets, moving target TSP, you see here. So it's a moving target search optimization. So there are some publications there. Also, we could compare the problem to an orienteering one. Why? Because, well, so we send the boats to collect these probabilities, right? So from these probability maps. So we send the boats. So as the boats collect probabilities, we could assume that these are the profits that are collected in an orienteering problem. So there's some resemblance there. Okay, so there's some resemblance with orienteering problems, but most of the literature are talking about path planning problems. And there are some, very recent actually publications. So it's still interesting. The problem is still interesting. What are the methodologies? Well, this is, quite common sense. So, so we need heuristics. So it's very hard to solve. And for real life applications, the territory is quite large, and the problem goes out of range for the exact method. Okay. So why we picked the constraint programming? Because the domain is discretized and we deal with the integers, the CP lends itself very well in order to be applied there. And also, there are some more operational realities, some operational constraints that are very easily incorporated into the SP model. So then we thought, let's give it a go. Okay, and we have given it a go, and I'm going to show you some results. Some assumptions. So the backbone of the problem is a grid of cells. So we discretize the whole area into a grid of cells. Now, these cells could be hexagons, could be squares. It doesn't really matter for the modeling. Okay, but yeah, it could be a hexagons. And that grid of cells will host the probability maps. The probabilities that I showed you before, that they move according to winds and currents, okay? So that probability map changes at each and every time slot because of weather, because of the wind. So there is a time horizon that we need to fulfill, that we need to complete our mission. And this is, let's say, in T capital time slots. Now, the vessels move from one cell to the adjacent ones, to the next ones, at each and every time slot. So we synchronize, let's say, the evolvement of the probability maps to the movement of the vessels. So these are synced. Or they could remain still. So even if the probabilities move around the area, the vessel might choose to stay still in a focal point so that they collect probabilities as the probabilities are moving around the vessel, and the vessel doesn't move. Okay, so there is still the option for the vessel to stay still. Okay, now we assume that the vessels hover up the probabilities as they move. So the moment that they visited a cell, we consider that they hover up the probability of that particular cell. As I showed you in this animation, well, the vessels here go back to the origin, but they don't have to come back. Just something. Okay, so they don't. So there are open routes. They don't have to come back. They don't have to come back. So these are the assumptions. Now, yes,
a quick question.
Yes, please.
So if your target is moving,
yes,
which is most likely the case, you have to be careful not to double count what you're collecting, because if your vehicle is moving and there's a probability that you find the target in one location and then you move in the direction where the wind or the waves will take it in the next time step. So if you move in the same direction that the target would be moving naturally in the next period,
very good point.
You'll be in the same spot. If you found it in the first period, you'll be in the same spot as the target in the next period again, and so on. So you have to be
very good point.
Measure the same thing twice or multiple times.
Absolutely, and we have considered that, and we have seen this happening, and that's why we believe that the particle representation enables a more accurate or flexible way to collect the probabilities. And I'm going to demonstrate that. So that's a very good point, and I have it in 2 slides. So I have an example in 2 slides. So what is this particle representation? Okay, so, and why do we need the particle representation? So so it comes with pros and cons. Okay, so, and I'm going to, present both. So what's happening? So when we have an incident, and let's say that this incident starts here, we have 100% probability of finding someone there. The truth is, though, that our boats and our rescue team is 1 hour away. So until we get the response call, so the rescue call, and until they deploy all the team and get there, and so it's usually getting 1 hour to get to the area. In that hour time, these probabilities are moving according to the wind. And if we represent the probability with particles, then these particles will be pushed around the area, okay? And the more particles per cell, the higher the probability, okay? The higher the probability of finding someone there. Now, So what does the literature do? The literature uses these particles in order to generate these probability maps. And as soon as they generate these probability maps, then they use the probabilities for their modeling. Now, what we say is instead of using the probabilities, let's be more specific and let's work with the particles specifically. So I need to know where each particle is at each and every point, and if they have been hovered up by our vessels, okay? So that's the main difference here in our representation, and we include that into our modeling, okay? So we explicitly know where each particle is. So let me correct what I said before, because I said that the vessels are hovering up the probabilities, okay? So I'm correcting it by saying that the vessels hover up the particles per cell. Yes,
that addresses my question.
Yeah, but I have an example in the next slide. So thank you for bringing it up. Does it help? Okay, does it help? We think that it's a more flexible way to represent the probabilities. There are some pros, and we will see that in the objective function. I'm going to discuss about that. And there are some also pros on extensions of the problem, and I'm going to talk about that as well. But on this particular slide, I wanted to show you an example. Let's say that we have an incident here, and the propagation happens. And according to this, wind directions, these probabilities are spreading, okay? Let's go back a few time slots. Let's say that this time slot is time slot t. And this is time slot t plus 1. So, and you see here that this particular probability has moved down because of the winds, okay? If we have a vessel that has hovered up this probability at time t, then this probability shouldn't exist here at all. By knowing which particles were there, and we know that particle 53 and particle 17 were there. So we know with their IDs. We will go and we will remove them from future time slots. Exactly as you said it. Thank you for bringing it up, John Francois. So we are enabled to have this dynamic update of probabilities for future time slots. Right. So the MIM notation. So we have a grid size of B by B cells. We have a number of time slots. We have the number of cells, the number of particles, K, vessels V, drones D. Now, the drones are assigned to vessels. So we have a subset DI of D that are assigned to our vessel IV. Even though these move independently, and I'm going to talk about that in a bit. So I'm going to skip that FB because I would like to talk about it when we will see the constraints. Okay, so I'm going to skip that FB and I'm going to describe what it is when the constraint comes up. So adjacent J is the adjacent cells for a cell J. And we said that a vessel moves from a J to the adjacent ones. Okay. Now we have adjacent square just to represent the second tier of adjacent cells because we assume that the drones run faster, travel faster. So instead of, the adjacent cells, the drones move from a cell J to the second tier adjacent cells. So they jump some kind of, because they move faster. We assume that they move faster. We have OJT, the set of particles that occupy cell J at time t. And this is our probability maps. This is, we know, so this is a parameter. We know that beforehand, okay? We know that beforehand. Now, this is an interesting one. I said again that when the vessel visits a cell, then they hover up the particles that exist on that cell. This is partially correct because, in fact, it doesn't scoop up all the particles, but only a portion of them. And why is that? Because of fog. Because it was dark and the visibility was very low. because of the noise of the tech that they're using in order to detect heat in the sea. Also, or altogether, just to reduce the efficiency of the team. And we have this parameter phi u for the vessels and the phi d for the drones. Okay, so separate. And we multiply that to the number of particles that exist on a particular cell, and then we scoop them up. Now, so this is terminology of the literature. So this exists. So probability of detection, this is how they call it. Now, I said that the vessels and the drones move independently, but we want them to have a maximum allowed distance at all times. And why is that? If the drone detects someone, they don't have the capability to rescue them, obviously. But the boat has to be in a close distance, in a short distance, so that they go very fast and they rescue them. Also, if the drone runs out of battery, for example, they have to be in a close distance to a vessel so that they go and they replace the battery or if they exhaust, something like that. So we allow them to move independently, but this is the maximum allowed distance between them. Something else, because the drone has a better viewpoint from above, we assume that, yes, the vessel scoops up the particles of the cell that they visit, but for the drones, they can scoop up the particles of the adjacent cells as well, because they have a better viewpoint from above. Okay, so they have a larger area to scan. The decision variables xi, jt. So vessel I visits cell J at time t. Same for the drones. And do you see now the y's? If vessel I collects particle K, so we know explicitly when we collected particle 57. So we know specifically, and we have that in our decision variables. The same for the drones. And time slot tk, do you see? So we record everything. So tk, the time slot that the particle k is collected. And the delta now, jt, is the uncollected particles in cell. This is a decision parameter. Why? Because, okay, so this ojt is the set of particles that exist in a cell j at time t. But this is a decision variable because vessels pass by, they scoop up some of the particles, then more particles come from the probability maps that they move according to the wind. So this thing the decision variable is an outcome of the vessel operation. Okay, good. Now, the objective function. We are trying to minimize the sum of the collection times for all particles. Small parenthesis there. This is what the literature does. So the literature has the probability of success. So they're trying to maximize the probability of success. So just think of a max in front of it, which is equal to probability of containment. This is what the literature uses as its terminology, which is the probability maps. This is a parameter. This is what we have as an input into the problem, multiplied by the phi, which is the probability of detection. So the more probabilities that the boats collect, the vessels collect, and the higher the probability of success, okay? And this is what they are trying to maximize. But in our case, not only we try to collect all particles, but we are trying to collect them at the earliest possible. And so in case we have fatalities, or if we have, very cold weather, this is very crucial. And I'm going to show you at the end how this could work, okay? In different variants of the problem. I can hear your process of thinking. So what's happening? Yes, please share.
If you minimize the time that it takes to collect all of the particles, you're not necessarily rewarding solutions that collect a lot of particles earlier on, right? So if you're trying to rescue someone who's fallen at sea, I think would favor a solution where you collect as many particles as possible, as early as possible. if you have two solutions that take about
very good point,
collect all of the particles,
very
you
good
want the
point.
one that gives you the most reward early on, so that you recover the person before.
Very, very good. So I fully agree. I totally agree. But is this not a non-linear?
I think so.
Yeah, that's the thing, right? But something that I haven't mentioned for the objective is that if the particle is not collected, because we might run out of time slots. We might run out of time slots, and there are some still particles in the area. If the particle is not collected, then it's equal to T capital. So we are penalizing the objective function with T capitals just to say, okay, well, you have to collect them. It's different to what you said, Jean-François, but still we avoid the nonlinearity. But that's a very good point, and we might explore that as well. So that's a very good point. Thank you. Thank you for sharing.
We tell people, sorry, we cannot rescue you because our model is nonlinear.
Yeah, that's a very good point. Okay, so we can deal with nonlinear. It's okay. Yes, yes, that's a very good point. Yes, thank you, Super. So yeah, a point taken, and so we will consider it. We will consider it in the paper. Thank you. So it's okay. So let's go to the constraints now. So it's particle K can only be collected once, either by the vessels or the drones. And I just explained the TK just now. So if we haven't collected particle K, it's TK equals to T capital, which penalizes that for the objective function. Now the movement constraint. So each vessel can only be at one cell at a specific point in time. The same for the drones. And the vessels move from T to T plus 1, move from SLJ to the adjacent ones. And the same for the drones, but they move to the adjacent square because it's the second tier. Now, the drone vessel distance constraint. So how do we know this DJ J prime? Well, we simply take the shortest path between us. So we count cells, okay, from a drone to the vessel. And this is how we preserve the maximum allowed distance. Now here, what we wanted to represent, so what we wanted to describe is that the amount of particles that we collect at each point in time, at each cell, is less or equal to the amount of particles that exist there. But from previous time slots, there might be vessels that are passing by, there might be other particles that are coming from the wind from other directions. So this is additional variable. So this is a delta JT. And the difficulty here was because the Y doesn't give us where we collected. So we know that YK, K is the particle, I is the vessel, T is the time. We don't have the cell there. And we want to connect the Y's to the X's, that's why we had to use some auxiliary parameters. Okay, so this is what's happening here for the vessels, and this is what's happening here for the drones. So it's less or equal, so the amount of particles that we collect is less or equal to the phi, to the probability of detection, to that fraction, to how many multiplied by how many particles are remaining on that particular cell. Okay. So now, so I'm gonna finish the description of the model by the turning restrictions, and here's when I'm gonna talk about the FB that I skipped during the notation. So what is FB? FB is a set of triples of forbidden turns. And what does that mean? When the vessel moves from, let's say, this cell to this cell, and it's actually moving, and these cells could be quite large areas. So to traverse that, maybe the vessel goes full speed, maybe. So if the vessel goes at a speed, they cannot have sharp turns. They cannot have sharp turns. So how do we represent that in our model? That was quite a pain, and I'm going to go through. So if we are here and there, then we cannot go there, there, or there. So the sum of the x's should be less or equal to 2. Okay, so we cannot allow them to be 3. The only allowable is this green arrows. However, we have to do that for all possible movements of the blue arrow.
Why can't you have sharp turns?
Because the vessel cannot turn when it's at a speed. So they can stop and they can have a 90 degrees. It's very, so a less than 90 degrees is very difficult to do. So just, physically, so, so they cannot turn. So they have to take a very long arc there. And if they do, they go that. So they go through the green arrow. Okay, so that's an operational constraint that we didn't think of, before, but it's quite real. But we're not proud of these constraints because it's an explosive number, and the MIP doesn't scale very well. Well, it scales badly. Yes.
This is very difficult. When you will be in Quebec,
yeah,
you can discuss this with Leandro. We are working with a product on something different.
Oh, wow.
Where you have these turns, it's very difficult.
Oh, Marlene, thank you. Yes. So I'm not happy with this.
Don't say thank you, because if you try to use what we're doing, it's very difficult. But I think just that constraint is.
It's terrible. I know. So I'm not happy with this. We're not happy with that. But somehow we had to incorporate that into the model. And I'm going to show you how the model scales and the results in a bit. Now, okay. So thankfully we have the CP that scales better. Okay, so I'm not going to go through. It's the same. So set of parameters are the same. All we need something new here is the position of particle K at time t. Okay, so that's the new thing there that we need to know as a parameter. Now the variables are slightly are different because the XIT has the ID of the cell. So the XIT is an integer variable. And let's say it takes the value of 23. And we have named the cells with an increasing number, so with an increasing counter. So we know that cell 57 is that particular cell there. And this is a variable. Okay, so it is the cell that is visited by vessel I at time t. The same for the drones. The Y's are the same with a MIP. Is the number of particles of the collider, and the TK is the same. So this is just the objective. That's nothing. So same objective, and the movement constraints, the drone distance constraints, and the turning restrictions are managed by a table constraint, which is how the CP works. And what's the table constraint? So for the table constraints, let me demonstrate. Let's say that we have two variables, x1 and x2. So these are all the possible values, combination of values that they can take. So, and we insert that into the CP, and that's one constraint. That's one expression. It's considered as, okay, so in quote marks, as one constraint by the CP. So this is why it scales very well. So we could have n dimensions on this table. And what we do here, we just put the allowable movements and we feed it into the CP as one expression. And this is why the table constraint just enables us to have a very scalable model. So these are all done, by table constraints. And the collection constraints are I'm not going to tire you with everything. They are very similar. Instead of the delta though, we have used O. We have used the maximum value. So that's not very tight. It could be done better by replacing the delta. Do you remember the delta of the MIP? So we had the delta here. The delta. So delta is the remaining particles in that cell. So we don't use that. We use the initial value. We use the initial value. Okay, so it could be tighter, but in order, again, to connect X and Y's, we had to use auxiliary values. So I don't know what's better. So we left it as this at the moment. We can do more experiments with the delta, but maybe it's worse if we use the delta here. Now, some auxiliary variables, eta, I'm not going to go through. So if the vessel is at the position of the particle, or if the drone is at the position of the particle, go and calculate the TKs, and the same for the detection probability constraints. Okay, so that's the phi, and we cannot allow to collect more particles than the ones that exist at that particular cell. That's all. That's all in terms of the models. And I said, an availability of data, we hope to get some data, okay? But at the moment, we have generated our own instance generation, generator. And I said that we played with the diffusion models. And if we assume that the tide can move by 10 knots, plus the wind, a maximum speed of 20 kilometers per hour might sound very high, but it's very realistic in severe weather conditions, okay? So that's the speed. So the cells, we have played with a number of cells for the grid up to 100 by 100. And how many time slots do we need for a realistic mission? I took that from that publication here. So this is the number of hours that the human beings can sustain, can be alive at sea, according to the temperature of the water. And you see here that, you know, for some very cold waters, we need to deploy 2 and 3 vessels and all the drones that we have so that we go to the territory and we start the search as soon as possible, because it's very crucial. The time is very crucial. That's why I think that the objective is going to work. It's going to work. But then we need as many people, as many particles. We don't know where the people are, okay? As many particles, the earliest as possible. Maybe a hierarchical primary and secondary objective, or we can discuss offline. But this is how. So this is how it works. So we have used 48 time slots, which is 4 hours, and 96 time slots, 8 hours, which is a reasonable mission duration. But missions can go up to days, right? So even 24 hours is quite reasonable. And I have some animations to show you that even if you send your vessels, you might not have enough time to. Yes, so you wanted to say something about
that your curve probably starts decreasing.
I know. It's not as easy as that. Yes, but I've just taken that from that publication, so it's not my.
That's 100 degrees.
Yeah, then they are burning. I know. When they are boiling, not burning. Yes. Absolutely. It's not as easy as that. Yes. But yeah, so you're going to play with a number of time slots, and if you decrease the number of time slots, then you need to have more vessels perhaps to collect more particles. So we played also with a number of particles. Why? Because there are pros and cons here. So how many particles are you going to use to represent the probability maps? The more the particles, the larger the particles, the more detailed is the probability map. But do you really care about how detailed the probability map is? And then I was thinking, so we're thinking there should be some kind of sweet spot there. But why is that sweet spot? Oh, yeah. So the more particles, of course, higher complexity, because we have them in our decision variables. So what we did, so we took a very large scale problem, 100 by 100, and we used 50 particles. And we used 100 particles. And then we compare the two probability maps for all time slots, and we counted some kind of Hamming distance. Okay, so what's the difference between and the difference was up there. Then we moved on to 100 and 500. The difference was by 1 point and onwards, as we initially thought, it doesn't pay off. We have diminishing returns. And we thought that sweet spot could be the 1,000. Okay. Now you might say, Dimi, for a different benchmark, you might get a different sweet spot. Can we just agree that this is just a pre-processing small step that it's worth doing before you run your models? I don't know how else though you would do that, Jean-François.
My intuition is that the right number of particles grows with the number of time periods. So the more finely discretize your time horizon, the longer it is, the more particles you need to be able to correctly represent where things may have scattered. So
very good point.
Complexity grows.
Yes, and the complexity grows
with the time horizon that you consider, because you need to have more granularity in the particles.
Yeah, and also if you have a very large grid, right? So if you have 500 by 500, this will spread very long. And if you have many time slots, then you expect the. So this is So this is a valid point. Yes, thank you for bringing that up. But somehow, so I'm thinking of that for the reviewers. So I shouldn't be saying that on the on the presentation, but that's what we think, right? So we want to have a solid approach. But that's the way. That's the way to deal with the problem of the number of particles. But that's an open thing. So that's an open thing. So we keep thinking about this thing. But so we fixed the number of particles to 1,000, and here are some results. I know that table is quite busy, but bear with me. So bear with me. So what are these numbers there? So 5 is the size of the grid, 1,000 is the number of particles, 48 is the time slots, and 5 is the severity of the wind. So that shouldn't be there at all. So that 5, but it's all 5. Okay, so we took a very strong wind. Vessel 1, vessel 2, vessel 3. So we used 3 vessels here. The MIP was able to solve that to optimality. Also, it found only one solution better than the CP. But overall, the CP is much superior, as you see. So the gaps are much better for the CP. But look at the scalability. So the number of constraints is almost steady for the CP because of these expressions, the table of constraints and the way that CP is working with the variables there and the constraints. So the MIP doesn't scale very well, so that's one observation. Also, the POS, the probability of success. Yes, we work with particles, but we can still calculate that probability of success, okay? Because we know where the particles are and when they were collected. So you see here that all the particles were collected here, the full probability, because we assume that phi equals to 1. Okay, the probability of detection is also 1. But for some instances, well, so here we had no particles collected. So the MIP couldn't solve that problem at all. Whereas you see here that the CP is producing at least, very good. It's not very good because of the gaps here, but it's producing some plausible solutions. Okay, let's increase that to 96 time slots. So we still see the same behavior, but the CP is much superior here. So as we increase the size, then the MIP steps back. The MIP just sits down. And of course, you see here that it wasn't able to solve these problems at all. Why? This is 96,000. This is the upper bound for the objective, because 96 is the time slots, is the capital T, and 1,000 is the number of particles. So if you sum it up, then all the particles have taken the capital T. So there was no particle collected. So the probability of success is 0. Anyway, so this is the kind of behavior that we see. And these results are with no tanning restrictions. I want to show you that. So we have tanning restrictions there and non-tanning restrictions here. And you can see so this is a suboptimal solution, of course, but you can see that visually how the solutions differ. We have 2 vessels here, 2 vessels here as well. So they try to scoop up the probabilities, but you see that the probabilities are already very, very spread, and they are unable to scoop them up. But this is impossible to deliver to the rescue teams. So this sharp turns. That's why we do not allow the sharp turns, and also, so you see the smooth turns are more applicable, right? But it comes with a catch. So on average, 5% more solutions in terms of the cost. But it's a price to pay because this solution, you cannot give it to your rescue teams. This, perhaps you can. And it's only for the solutions that we found the optimal solution. Okay, so it's on average 5% worse. And I'm going to show you that in the next table. So we only accounted for these 3 that we got the optimal solutions. That's why we calculated that 5%. Okay, so but this is yet to be revisited because we don't have all the solutions solved optimally, of course. So you see the gaps there in terms of the cost of the solution. Again, look at how the MIP scales in terms of the turning constraints. So we're talking about 30,000 more constraints here, Marilyn, and only for the turning restrictions, which is terrible. So I'm not happy with that, but we have to find a way to incorporate these constraints into the game, and this MIP with and without. Okay. To the contrary, the CP, you see how the CP behaves. So yes, we have more constraints there, but it's very scalable. It's very scalable. And then again, we have much better solutions. So we are happy with the behavior of the CP, but then again, there's still room. There's still room for us to do more things. Right, last slide. Thank you for your attention. Last slide. So what if we have fading probabilities? What if your particles will not be there forever for you to collect? That's why we believe that the new objective of picking them up as early as possible will work much, much better when we have fading probabilities, when we have fatalities, because of the cold weather or the cold water. So the new objective here helps, which is enabled by the new representation, the particle representation. What if we have multiple incidents? What if we have 3 different focal points? By knowing that particle 17 belongs to incident 3, we will be able to play with equity, equal treatment of different incidents. Because if we don't incorporate that explicitly, the solution that we might get is collect everything from here, and this will be neglected. So by knowing that each particle belongs to different incidents, then we will be able to balance them, as we do with the balancing VRP, with the load. So the equality to the drivers, or the equality to the loads, the balanced VRP. So again, the new representation helps. Something else so there's so much room there because there's so many redundant variables. So yes, we have the probability maps. Yes, we know that the probability maps move there and there. And there's some empty areas, which we could exclude. But these empty areas, our vessels might want to traverse. So we cannot explicitly exclude that because the vessels might want to pass by this area. And yes, you might have that empty space here, but the vessel might want to move from here to there. So if you don't have the variable, so they won't be able to move. So we are hoping for some heuristic, reduction of the variable. Even though we compromise the optimality, we want to solve larger scale problems. And what we're thinking is just to work with synergies between AL and S. We have done something similar in the past, right? AL and S with the CP, but something more powerful for larger scale. Okay. So that was my last slide. Thank you so much for your attention.